Well, thank you very much. I felt an obligation to squeeze the word determinant into my title. So to do that, I had to think of a theorem which would have the determinant in it. So that'll come at the very end. And I'm going to talk about work I've been doing in the last few years with Kai Behrendt about deformations of complexes of holomorphic vector bundles, and so this is a slightly new result about the determinant, but it's not anything too special. So happy birthday, Jean-Michel. And you know, if you want to think about things to say about Jean-Michel, I mean, I'm not much good at words, but I would just like to repeat what Jean-Benoit Bost said last night. He was comparing Jean-Michel to Haydn. And you know, the more I think about that comparison, the more just it seems to me. I really like that. So I have known Jean-Michel for a very long time, and I can't imagine actually my life without knowing him. So the determinant, I never really appreciated it until recently. I guess it was Grothendieck who emphasized that the determinant of a complex of vector spaces is actually well defined even if you change the complex to a quasi-isomorphic complex. And it turns out to be a tiny bit thorny to get that straight. It took Grothendieck and Mumford to sort that one out. So it's not a utter triviality. So let me just re-emphasize. The definition of the line that you associate to the complex is, of course, easy. Most of us here know how to do that. The problem is, if you have a quasi-isomorphism between the complexes, to make sure that there's a natural isomorphism between those two lines. So I'm going to talk about this formalism that I've been working with. The goal is to understand higher stacks. So the usual stacks are one stacks in this story. And in this world of higher stacks, I'm going to give a specific approach which will render the definition of the determinant pretty straightforward. So that's a sort of advertisement for this approach, and I'm optimistic that it'll have more important advantages than this one. This is just a little step along the way, but it does have the advantage of having the word determinant in it. So, so I'm going to show you that if you have a complex of length n, so on a compact complex manifold, you begin at E1 and end at En, then the deformations of that will be an n stack. I'll try to explain. I'm going to define for you what an n stack is, don't worry. So I'm going to be working in the analytic setting, and I'll have an analog of Kurenishi's construction in which he shows how to use the actually a kind of gauge condition to cut out a finite dimensional n stack. So, and actually the hardest part of that work is the definition of what an equivalence of n stacks is. So I'll rush one slide past you in which you'll see what it is that one has to check. And finally, I'll show how the definition of the determinant naturally can be made on this n stack. And so I'm working with Kai Behrendt, who's at University of British Columbia. So I want to start with the following, which all of us know. If you have a Banach algebra, then the invertible elements of the Banach algebra form an open subset, and that open subset is a Lie group, right? If you insist, I'll put the word Banach in front. It's a Banach Lie group, but it's a Lie group. So that's an example of a one stack. The nerve of, or the classifying space of a Lie group, BG, is an example of a one stack. It's the quotient of a point by the trivial action of the group. And so what I'm going to explain is how much more generally we can view this example. So we have a differential graded Banach algebra, and what is the group of units of that differential graded Banach algebra? So I'm going to explain to you that if this differential graded algebra is concentrated in degrees greater than -n, then we're going to get an analytic n stack, and I'm also going to use the words Lie n groupoid for that, because again, the formalism of one stacks I'm going to use will identify with the theory of Lie groupoids, which is a I think they were invented in France by Erasmus. So in fact, what we're going to do is work with simplicial Banach analytic spaces. Banach analytic spaces, introduced by Douady, are a very convenient framework. They include analytic spaces, they include Banach manifolds, they include very many things. They are closed under finite limits. It's a very nice category to work in. And you can define surjective submersions between Banach analytic spaces. That is, you can say which functions between Banach analytic spaces are surjective submersions, those which locally look like the base times a ball in a Banach space. And I'm going to be using surjective submersions of Banach analytic spaces a lot. So let's go back to the nerve. This is a construction, I don't know who it's due to. Sometimes people say Grothendieck. If you have a natural number n, you have a very simple little category here where the objects are numbered 0 to n, and you can hop up but not down. Okay? And you can take this little category and look at all functors from this category to the group G. A group is a category in particular. And you get a set of n simplices. They're just, I should have written this on the slide. There are all sorts of things that aren't on the slides. So between I and I plus 1, we imagine that we have an element of the group. And so we just have a sequence of elements of the group. This is a fancy word, this set, for the nth power of the group. So in particular, the first few of these are easy to identify. N0 of G is the identity element, in a sense. N1 of G is the set of elements of the group. N2 of G, we'll see, is in some sense the multiplication table. So all sorts of things that fit into group theory find a very elegant interpretation. Maybe I shouldn't overemphasize the elegance, but I like elegance. So, and I also wanted to make a note that this looks like it's infinite. I've got pieces of the nerve for every natural number. But in fact, if you're only interested in groups, you only have to go up to n equals 2. That contains all the information. So you can just keep a finite amount of data. And you could also do this with groupoids. Actually, you can do it for any small category. And in the case of a groupoid, the set N0, the set of vertices, will just be the objects of the groupoid. So I'll say a bit more about this on the next slide. No, I've got a couple more slides to go. So I have to talk a bit about some explicit simplicial complexes. So this part of the talk is due to Dan Kahn. He introduced these explicit subcomplexes of the n-simplex. So the n-simplex, okay, if you know about simplicial sets, maybe I should say I say it in a different way. The n simplices in the n-simplex they are increasing monotonically, weakly increasing sequences of integers between 0 and n. We have I0 up to Im. And if you have strict inequalities, those are what are called non-degenerate simplices. So when you form the geometric realization of the simplex and you get just a geometric simplex, the ones you actually see, the ones that have the m simplices that are actually m-dimensional are the non-degenerate ones. there are only a finite number of those. So 2 to the n plus 1 minus 1 in all different dimensions. Okay? So the ith face of the simplex is the affine hull of the convex hull of all of the vertices except the ith vertex. All right? And the horn, lambda ni, that's the union of all the faces of the simplex except the one opposite the ith vertex. So it's the union of all the faces of the simplex containing the ith vertex. This is probably the hardest moment in this talk. So, so if you find this hard, I'm with you. It must be horrible to be seeing this for the first time. But bear with me, or just do something else. I don't know. Okay, so if you have a simplicial set, or a simplicial analytic space, you can take all the maps from the horn to this simplicial set, or simplicial space. And you get a set, or an analytic space, respectively. So what is it? What I'm saying is I'm going to take an n-1 simplex in X for each of the faces that meet the ith vertex, and they have to glue together along their common n-2 dimensional common faces. And so it's a nice array of n-1 dimensional simplices. There's a total of n plus, there's a total of n of them, and we also are missing the interior. Now, if you have an n simplex, you can just take all the faces except the ith face, and they will glue together to form a horn automatically. So we can look at that map from one to the other. And so for sets, it'll just be a map of sets, a function of sets, and for analytic spaces, it's some map of analytic spaces. So, and then I've given a name to the map, lambda ni, because for the next few slides, it's going to occur quite a lot. So the special case, n equals 1, is very easy to understand. So let me... So for n equals 1, let's take lambda 1, 0. So that goes from the 1 simplices to, well, what's lambda 1, 0? Well, so if this is the 1 simplex with vertices 0 and 1, so this is lambda 1, 0. It's actually the first vertex. Oh, sorry, I got it exactly the wrong way around. Go. Try again. Okay, I'll cheat. Okay, it's the lambda 1, 1 is the first vertex. So this is x0, right? And so what are we doing? This is the target. And in fact, my slide is wrong. The next slide is switched. Oh, no, it's right. Okay. So lambda 1, 1, this is the target map. It takes our one simplex, thinking of it as a morphism in some groupoid or something like a groupoid, it takes it to its target. So that's very nice that these maps are capturing, at least at the 1 simplex level, some notion of source and target. And so the idea you should keep is that at the level n, where the n simplices will be some sorts of n morphisms have n plus 1 sources and targets, labeled from 0 to n. That's at least this perspective on what an n morphism is. I'm juggling too many things. Okay, so here's an observation of Grothendieck. I have absolutely I think of it as an observation of Grothendieck, but I have no idea where it is located. So you can actually single out the nerves of groupoids. Remember, I defined nerves on the previous slide. If and only if these maps that I've defined are bijections for n greater than 1. If they were bijections for n equals 1, that would be saying the source and target maps were isomorphisms, and so actually our simplicial set would be a set. All right? That would be the zero case of this observation. And this is, to me, the best axioms for groupoids. So we're going to generalize this characterization. And if you wanted to know what groups were, you just have to impose an additional condition that there's only one point in x0. So that replaces the first chapter of the undergraduate textbook on algebra.
You use your statement that beginning with dimension 2, everything is determined by
Completely, yeah. Yeah, because of these being bijections, you can read off what x2, x3, and so on are, and not only that, but you can show, I'll show you actually the next, good, right. So here are a couple of examples from 2 dimensions now, and so suppose this is a horn actually for a groupoid. It's got the element, a 1 simplex G on so that's actually the second face, and it's got an H on the 0th face, and now let's try to fill it in. So how would you fill it in? I did it wrong on the slide. I apologize. I wrote GH. The answer, of course, is HG. Yeah, it's the usual. Yeah, oops. Okay, so Francois, I'll modify the slides before you put them online. So you see, we filled in the horn in this way, and it was a bijection. So the isomorphism, lambda 2 being an isomorphism, is the statement that we have a multiplication table. What about inverse? So this one, nope, I got this one wrong too. So there, anyway. So the correct answer is H times G inverse. And, yeah. Oh well. So the point is that we can read off the multiplication and inverse maps from Grothendieck's condition at n equals 2, and associativity would have been the n equals 3 case, but the slide gets a bit complicated, so I skipped it. So you can generalize this theorem of Grothendieck considerably. So in particular, you can actually characterize the nerves of categories by throwing away these maps for I equals 0 or I equals n. So if we go back, we keep the top one, but we don't keep the bottom one, right? And indeed, the top one was about multiplication, but the bottom one was about division, and we throw it away because it has I equals 0. And so that's a cute observation, but, and that would be a whole different lecture, but I'm most interested in the following point. Suppose I was interested in this theory of Lie groupoids. How does that fit into this framework? So in fact, you should impose some additional conditions. So you keep Grothendieck's conditions for n greater than 1, that we have isomorphisms in the category of analytic spaces, or manifolds, if you prefer. But for n equals 1, we have the source and target maps. They should be surjective submersions. Okay? So that's exactly the definition of what a Lie groupoid is. It's a differentiable groupoid whose source and target maps are surjective submersions. And so let's generalize that. So here's, in the discrete case, a definition of n groupoid due to Duskin. And in the smooth case, it's due to Enriquez. And I'm going to take it all the way to Banach analytic spaces. So first, in the case of sets, a K groupoid is a simplicial set such that these maps are surjections for all n greater than 0 and for all I, and bijections for n greater than k. That turns out to be a very convenient generalization of the notion of one groupoid. And actually, for k equals 2, it agrees quite closely with Benabou's notion of a bigroupoid. It's not exactly the same, but it's a convenient replacement for it, and not terribly different. And a Lie K groupoid, we replace sets by Banach analytic spaces, and we replace surjection by surjective submersion and bijection by, diffeomorphism. No, that's correct. Isomorphism of Banach analytic spaces. So that's the main definition of this talk. All right? So I'm going to produce lots of examples. That's the point of the talk. If I didn't have any examples, there'd be no reason to give this definition. So, so now, when I said at the beginning that if I have a differential graded Banach algebra, I'm going to produce one of these, that's exactly what we're going to do. Now, so if you think back to Kodaira and Spencer's theory, they were looking either at deformations of a algebraic variety or a complex manifold, or deformations of a vector bundle, and they expressed those in terms of, well, in the case of a vector bundle, a certain element of a differential graded algebra satisfying a certain equation, which is the same equation that we're familiar with in differential geometry for a connection to be flat. So it's called the Morikawa equation. And so now let's just abstract it to a great degree and take an arbitrary differential graded algebra and an element mu of degree 1, and then its differential will have degree 2, and its square will have degree 2, so we can add them together, and the equation is that they should add to 0. So it's a quadratic equation, all right? And so we can define a new differential on the complex of vector spaces underlying the differential graded algebra. We take I should have said this more carefully. We take the original differential, and then we take the graded bracket with mu. So if I apply this operator to an even degree element, it's just the usual commutator with mu. But if I apply it to an odd element, it's actually the anti-commutator. And in that case, we get this beautiful result that the Morikawa equation implies that this deformed differential has square 0. So that's why we know about this equation from the theory of flat connections. And so I'm going to say that if I have a differential graded algebra, the set of all Morikawa elements I'll denote by MC of A. And if I have a Banach differential graded algebra, then I get a Banach analytic space. Now I always get confused at this point because at first you might think that this is an algebraic equation. But, well, it's quadratic, but it doesn't take values in the complex numbers. It takes values in a Banach space, A2. And so perhaps in some versions of algebraic geometry, that might be considered to be an equation, but it's not the sorts of equations that algebraic geometry studies. Algebraic geometry studies complex equations. This is a Banach equation, roughly. So we don't use the methods of algebraic geometry to study the vanishing locus. We use the methods of analytic geometry. So I'm going to give an example of a differential graded algebra, which may need to fix notation. So this is going to come from taking a check nerve over a space and then looking at check cochains. And so I have to remind you about the Alexander-Whitney or cup product and the differential. So this is just from our undergraduate course in simplicial cochains. So the normalized check complex for this cover, so I'm going to, now we come to a subtlety, I'm going to use the unordered check cochains. So this is a complicated story. Often when we learn about check cochains, we use ordered check cochains or alternating check cochains. And on the other hand, then when we, say, turn to Iluzi's book or something, we suddenly see unordered check cochains. And I've got to tell you that when I was a student, I found this contrast very confusing because, in fact, the relationship between these two complexes is difficult to understand. I've just learned through the power of Google that the isomorphism was established, in fact, in Sayre's paper on coherent sheaves. So it goes back a long way, but the calculation is very implicit. It uses the acyclic model, what's that called? The theorem of acyclic models. Anyway, I won't need that today. So here is the definition of the check cochains. And by normalized, I mean I've thrown away the degenerate ones. So that's why I put that consecutive indices are not equal. Okay? And here are the differential and the product. The differential begins with the internal differential, and then it has the standard differential on check cochains, the check differential, and the product is the Alexander-Whitney product. So, oh, except for the misprint. This is P here, okay? I've got I have a pointer, don't I? Yeah, that's meant to be P. So, so don't panic. Oh, and that's meant to be Q. Okay, that didn't work so well. No, oh, and that's meant to be Q. Okay. No, actually, that's meant to be Q, that's meant to be 0, and that's meant to be Q. And then it would have been correct. Okay, I need to work on that formula. Okay. But the idea is that from a simplex, from a sequence of vertices I0 up, or a sequence of open sets in the cover, I0 up to Ik, we take the first P plus 1 and the last Q plus 1, and they overlap. Oh, God. Oh, sorry. Let me try again. There are too many. It's just, you can't save it on the screen. Yeah. So.
All that is on YouTube, don't worry.
Yeah. So the idea is that we use the first P plus 1 open sets in the cover for the left guy, A, and the last Q minus P plus 1 sets in the cover for the second guy, B. So that's the definition of the Alexander-Whitney product. And I'm going to take a very trivial case of this, but an interesting one, in which I take the geometric realization of the n simplex. So this is, don't worry about that actually, just imagine that we can take open sets where we remove the ith face. So that leaves behind an open subset, and that gives a cover of the n simplex, and it's quite an interesting cover. It'll play a special role. So here comes a extremely confusing notation. I want to study a simplicial set, which I'm going to call the fat simplex. And it's like a juiced up version of the ordinary n simplex. It's very hard to visualize geometrically. In fact, I haven't succeeded. I'm beginning to. If you know what the zero co-skeleton is, you'll be able to verify what I'm about to say, that just as the non-degenerate simplices of the n simplex were monotone increasing sequences of vertices, the simplices of the fat simplex are just arbitrary sequences of vertices such that ij does not equal ij plus 1. Okay? So it's infinite dimensional. Obviously now we can form arbitrarily. M is not restricted to being less than or equal to n. So these are the non-degenerate simplices. So roughly speaking, this theorem that I mentioned, that you can use either the ordered or the unordered check cochains, comes down to the fact that this simplicial set is contractible. And you've got to invent some way of proving that. And that's what Serre did in his, roughly speaking, that's what Serre did. So the single case I can understand is delta 1, which is sometimes written in the quasi-category literature J. And think about its geometric realization. It actually is an infinite dimensional sphere. And the infinite dimensional sphere is, in fact, contractible. So that's just the easiest case past n equals 0. N equals 0, delta 0 and fat delta 0 are the same. Okay? And I've shown you what the two non-degenerate simplices in each dimension are. They're the ones that go 0, 1, 0, 1, 0, 1, and the one that goes 1, 0, 1, 0, 1, 0. Okay? So I'm going to take, if I'm given a differential graded algebra, the check cochains on the n-simplex with this cover that I told you about, and with values in the complex of vector spaces A. So that's actually a differential graded algebra, because on the one hand, the check cochains are a differential graded algebra, as I showed you, and on the other hand, A is a differential graded algebra, so we just have to combine those things together. So it's exactly the same thing, though, as the non-degenerate simplicial cochains on the fat simplex. So I'll write it in that way for the rest of the talk. Okay? So I've got to drag you through a certain amount of explicit detail now on what this looks like. But now comes the main definition of the talk. I'm going to define for a differential graded algebra a simplicial set called the nerve of the algebra by taking as its n simplices the Moré-Cartan set of this differential graded algebra. So I have to justify for you why on earth this is the right thing to do. All right? It is, however, very compact, the definition. Now let me actually unveil the explicit formula for what an n-simplex is. So it's this collection of elements of A. It'll have the point is that it'll have elements like this, A0 up to AN. These are elements of A1. And then it'll have elements Aij, where I is not equal to j, and these will be in A0, and I'll leave a little vague what comes after that, because it would get too complicated to explain. But there's quite a lot of detail, and I'm going to unpack this for n equals 0 and n equals 1, because otherwise there's not much point writing it on the board. But just for completeness, I've given the explicit definition. All right, so a zero simplex, that's just an element of the Moré-Cartan set, because the fat zero simplex is the zero simplex, and in fact, its cochains are just nothing. They're the underlying field. So, so the vertices of this nerve are the Moré-Cartan set of A. Okay? Now, what's a one simplex? Well, so remember I said there are only two non-degenerate simplices in each dimension, 0, 1, 0, 1, 0, 1, and 1, 0, 1, 0, 1, 0, 1, and so on. Okay? So roughly speaking, in each dimension we have two pieces of data. In each dimension, A1, A0, A negative 1, and so on. And then there's some quadratic equation relating them. So I'm going to unpack things in the following way. A0 and A1, they're the source and target of my one simplex, and I'll just call them mu and nu, and they're a pair of Moré-Cartan elements. Okay? And I want to think of this one simplex as a morphism from mu to nu. So let me define a morphism as, so a morphism just in a more abstract sense between Moré-Cartan elements is an element of A0 which intertwines those differentials I introduced. So that's meant to be a more geometric understanding of what a morphism is, and I can construct a pair of morphisms by adding the identity element to A01 and to A10 respectively. You can check, if you go back a slide, if you're bored, you can check that that bottom equation in the special case that k equals 1 amounts to these equations for f and g. Okay? So in particular, we have this pair of morphisms, f and g. And if the algebra doesn't have any negative degree elements, that's the end of the story. But let's go on. Let's suppose the algebra does have some negative degree elements. There's an important concept of a quasi-isomorphism, which is where you have an element f, you've got an element g, they're both morphisms in opposite directions, and the two compositions, gf and fg, are homotopic to 1. With homotopies, which are part of the data, well, they're not part of the data for the quasi-isomorphism, but they're part of what has to be given in order to know we have a quasi-isomorphism, and there are two homotopies, H and K. And sure enough, if we have a 1 simplex in our nerve, we have such homotopies, A010 and A101. So actually, both F and G are quasi-isomorphisms when we have a 1 simplex in this nerve. And so actually you can prove this stronger theorem that it's if and only if. I had the proof was a formula, and I decided to take it out because it was a little scary. But it's this is not a very difficult idea. I guess we can ascribe this to Martin Markel, who doesn't formulate it at all in this way, but has all the calculations which go into this theorem. All right? So let me just emphasize, if you have a morphism, you could ask, is it a quasi-isomorphism? And the answer is, if and only if it lies in the image of the map from the 1 simplices in the nerve into the morphisms. And this has an interesting corollary, that if you have a differential graded Banach algebra, you can ask about the set of all quasi-isomorphisms. And it turns out they form an open subset. And that, of course, generalizes the statement that the isomorphisms in a Banach algebra form an open subset. And as far as I know, nobody noticed this before. It's essentially the same result, but with a little bit of homological algebra twist to it. Okay, so in particular, we can ask what happens if our algebra doesn't have any negative degree elements. So in that case, f and g, if we go back, they're inverse to each other because the left-hand side of these equations are 0. So we see that the 1 simplices are just precisely the invertible elements of A0. All right? So actually, the correct way to say it, if you know about the Deligne groupoid, is that in this case, the nerve of A is associated to the action of this group, the invertible elements of A0, acting on the Morat-Cartan set by a certain action that Deligne wrote down. It's essentially the gauge action of a gauge group on the space of connections. And in that case, we get a canonical isomorphism between the n simplices and the Morat-Cartan set crossed with the nth power of this group. Okay, so another example where an example of that, in fact, is where we look at the moduli stack of vector bundles. So in that case, we have a very simple differential graded algebra. I've got a Stein cover of a complex manifold, and I take just basically holomorphic functions, the sheaf of holomorphic functions, n by n matrices of holomorphic functions, and I look at its the check cochains, normalized check cochains, and apply this nerve. So the Morat-Cartan elements are the vector bundles trivialized with respect to this cover. And the gauge group, the units are the gauge transformations, all the transformations between those co-cycles, those trivializations. And we recover the moduli stack of vector bundles then as our nerve. So this recovers something that's well known. And now I'm going to propose that if we apply it to things which are less well known, it's the right answer. All right, so now what about the general case? So here's the main theorem of the talk, that if we generalize what we had before, I should have, forget the second bullet. So if the differential graded algebra vanishes below degree negative k, then the nerve is a k-groupoid. And if it vanishes above degree 0, in addition, then it's actually a k-group. Let me write that in a different way here. So if we're in degrees minus k to infinity, then we get a k-groupoid. And if we're in degrees minus k to 0, we get a k-group. Right. And in the Lie case, if we had a differential graded Banach algebra, and this is a considerably more difficult theorem, then we get a Lie k-groupoid. Okay? So actually, the hard part of proving this result is proving that the source and target maps for one simplices are surjective submersions. But actually, given what I've told you, you can come up with, using the implicit function theorem, which is, of course, your only friend here, you can do this in a straightforward fashion using the explicit data of the quasi-isomorphism that I've given you. So it would take a bit long to explain the proof. If I had a second hour, I'd give you the explicit proof. So, as I say, the one simplices are now quite complicated. They're quasi-isomorphisms. Now, I should say that I've, yeah, okay. Now we come to the main example. So I'm going to use the Dolbeau resolution of endomorphisms of a complex of holomorphic vector bundles. So this is, I'm now shifting gear completely. I didn't have, I don't know how to make the check complex into a differential graded Banach algebra. So I don't know how to put the algebraic story or the analytic story directly into the Banach world. But by using Dolbeau resolutions, I can do that. Oops. Okay. So the context will be, we have a compact complex manifold X and a complex of holomorphic vector bundles of length n. Up till now, we were talking about length 1, just a single vector bundle. And I take the differential, the differential graded bundle of differential graded algebras, end E, and I take its Dolbeau resolution, the 0Q forms, and I have to be careful here. I'm going to take the 0Q forms with coefficients, not smooth coefficients, but with coefficients in a carefully chosen Sobolev space. It's not that carefully chosen. It's of regularity S minus Q, and now the theorem is if S is greater than the complex dimension of X, then this is actually a differential graded Banach algebra. It's not my theorem, but it is a theorem. Okay? Actually, I have no idea whose theorem this is. The literature on Sobolev spaces evolved kind of slowly, and even if you look in the 60s, I think in proof, or maybe 50s, proof of the Newland and Nirenberg theorem, I don't think that the authors were quite sure of the strictest. This is the optimal result.
You mean the Dolbeau complex of the holomorphic bundle and...
I'm sorry? The whole complex, 0 to...
The Dolbeau complex.
with that regularity. So the regularity shifts depending on Q. Yeah. And so you have to check two things. You have to check that the product works, and you have to check that well, it's obvious the differential works. So actually, something very close to this is in one of the appendices of Donaldson and Kronheimer's book on gauge theory. So this is, in fact, for people who study connections, this is a fairly well-known thing. And this is a bit complicated to explain, but I'm sticking in the exposition here today to a single complex of vector bundles, but really I should be considering lots of different complexes of vector bundles and setting up a groupoid between quasi-isomorphic deformations of these different vector bundles. So I'll just, for the purposes of exposition, do the case of a single complex, but there's much more. It's a much broader theorem than this. So let's take the nerve. By my theorem, that's a Lie n groupoid. So those are my main explicit examples of Lie n groupoids, and they're completely new. This is a sort of kind of pioneering. So the problem, of course, is that this is very infinite dimensional. I haven't cut this down, so you can't really compare it to corresponding results in algebraic geometry. So in algebraic geometry, as I'll say a bit later, so Hirschowitz and Simpson constructed similar algebraic n-stacks. They called them, I think, geometric n-stacks. And if you wanted to compare them, I should confess I haven't yet succeeded in comparing them, but if I want to, then I should be cutting my Lie n groupoid down to finite size, right? And that should be using some sort of elliptic regularity. So if we go, oops, okay, the bottom line is invisible. If we go back to Kurenishi's work, he was working in the setting of a single vector bundle, and he essentially imposes this gauge condition, that the divergence, the adjoint of the d-bar operator applied to the terms in the gauge, in the Moret-Cartan element, are 0. So the details are not so important. We just need a supplementary elliptic condition. And I have to confess, I'm simplifying greatly the construction that I really want to do, because I should do this at different parts of my stack. This is just what I would do around the 0 Moret-Cartan element. But there are going to be similar conditions at every Moret-Cartan element in my stack, and I'm going to take the union of lots of different pieces. So do I have time for this? Yeah, barely. This is, I just want to run over the definition of what an equivalence of Lie n groupoids is, because this is new. So maybe I'm going to draw a picture for, so this is delta 1, 2. So it's, the product of the 2 simplex and the 1 simplex, okay? And then, so what is this prism in it? So the prism, so let's try to illustrate lambda 1, 2, 1. So it'll contain this end, because that's in the delta 1 direction, that's the first vertex. And it'll also contain all the longitudinal stuff that lies over the boundary of the 2 simplex, and now you can see why I'm not in art school. It's kind of like a cup. I've gouged out the interior of the prism. I've taken off one end, but I've left the other end, okay? And in higher dimensions, it's not an end that we leave, but it's a horn, okay? But I only need the case, actually, I only need the case n plus 1 here. So, anyway, the condition is a tiny bit complicated, but in any case, it has the same flavor as the condition to be a Lie n groupoid in the first place. So if I can say a little bit about what it says that I have a map from the whole prism to y, and I lift it to x along the cup, and now I'm asking about all the fillers in Y together with a lift at one end to X. It's kind of a lot of data, but when the dust settles, it's that all of those maps should be surjective submersions that is the correct definition of equivalence of Lie and groupoids. And you can prove that compositions of equivalences are again equivalences, and they also have this cancellation property. If the composition of two equivalences is an equivalence, then if either of them is, the other one is. That's, of course, a property that homotopy equivalences have in topology, and or weak homotopy equivalences have, I should say. And in the case of Lie zero groupoids, we just get isomorphism. All right? In the case of Lie one groupoids, we get the usual notion of equivalence of Lie groupoids. So this is another part of our work to make this definition. And then the theorem is that if you impose the Kuranishi gauge, you get a finite dimensional substack equivalent to the whole thing. So this puts Kuranishi in a higher stack context. Right? And so now the final topic, determinants. So as I wanted to express the hope, I guess, that this is a analytic analog of the constructions of Hirschowitz and Simpson. It's now incumbent on us to compare our results to theirs, and even better, to the derived versions of Toen-Vaquier and Bezzossi. Okay, so finally, what about the determinant line bundle? So I should explain to you a little, what are these deformations that my Lie n groupoid is parametrizing? They're not actually deformations to complexes of vector bundles. They have some higher form pieces. So the Morikawa elements have a 0 form piece, a 0,1 form piece, a 0,2 form piece, and so on. And the 0 form piece is just a deformation of the differential of the complex. But it's not holomorphic. The 0,1 form piece is like a deformation of the complex of the holomorphic structure of the individual bundles in the complex, but they don't necessarily satisfy the Kodaira-Spencer equation, the Morikawa equation. But the 0,2 form piece expresses the error. It's a homotopy for the error in the Morikawa equation. And so I guess I first really met such twisted deformations in the papers of Bismut, Gillet, and Soulet, where at least the process rather remarkably terminates at q equals 2. You don't have higher ones. But if you want to study higher stacks, you're really forced to include the higher ones. It's not really sensible, at least in this formalism, to truncate. Okay, so now finally, we come to the problem of defining the determinant in such a way that it's natural for quasi-isomorphisms. So I'm going to interpret that as asking that I have an n functor, if you like, from my Lie n groupoid to the groupoid of line bundles, holomorphic line bundles on my manifold. Another way of saying it is I have, in fact, a simplicial map from this nerve to the nerve of the Picard groupoid. So let's see. So Knudsen and Mumford, if you look in their paper in Mathematica Scandinavica, they do it by locally, they choose frames. So they use bases. I was teaching complex analysis, and on the first day of the class, I chose a coordinate system, and one of the students left and never came back. So there is a school of thought that we shouldn't use frames. So Knudsen in 2002 remedied that. He gave a much more natural construction in which he didn't use auxiliary choices like bases, but rather gave a direct construction. And so I just want to remark that his auxiliary data turns out to be isomorphic to the additional data that's present in today's definition of a one simplex. So the correct proof that a quasi-isomorphism leads to a natural isomorphism of determinant lines comes automatically from today's definition of a one-simplex. So I'll just show you the formulas that show that. So we recall that the determinant is given by this alternating top exterior power. So that's a line bundle, and we deform its holomorphic structure using mu1. And that does, in fact, satisfy the Morikawa equation. And then finally, if we have a quasi-isomorphism, which comes from a one-simplex, then we can read off the data that we need to construct the canonical trivialization of this ratio of determinant line bundles. It's obtained by taking this particular matrix. So this has G, the quasi-inverse in the lower left corner, the two homotopies on the diagonal, and one extra piece of the story up above the diagonal. And if you look in Knudsen's paper, you'll see he needs something in there, but we have it automatically. And just to remind you, this is how they're explicitly constructed from the data of the one-simplex. And the point is, this turns out to be a contracting homotopy for the deformed differential. And when you have a contracting homotopy for a complex, sorry, this is the differential on the cylinder. So we're trying to trivialize the determinant of the cylinder of this morphism, and to trivialize the cylinder, to trivialize a determinant line, you just need a contracting homotopy, and then it's a canonical construction. So that shows that on our nerve, this particular Lie N groupoid, the determinant is defined completely naturally without any choices. And so I'm optimistic that this is another small sign that, that this is the right definition, at least in analytic geometry. And so let me just finish, of course, by saying how excited I am to be able to participate in this week's festivities.